Okay, last time we were into gases and gas stoichiometry, and we did a number of different types of examples with gas stoichiometry. Remember that it is really just really a stoichiometry problem in most cases. The additional thing that you need to do is at some point probably use the ideal gas law. So you might use it up front in the calculation, and in that case, you probably would be solving for moles. And kind of that second step where we get to everybody into moles. But very commonly, you kind of use it on the back end of the calculation, where we kind of typically usually go from moles back to some other unit. And in a lot of cases, we'll use it to figure out the volume of the gas that we generated. So the next thing we're going to talk about is partial pressures and the law of partial pressures. And Dalton's law of partial pressures sounds really difficult, but it's sort of a pretty straightforward idea. One of the things that we talked about as something being an ideal gas is the idea that pretty much there'll be no interaction between that gas and other gases. They're not really attracted or repulsed by each other. So when we have a mixture of gases, which is how they usually will come, if we have in one container, for example, just A and one type of gas, then the total pressure of that particular container is a result pretty much of only pressure of the gas molecule A as they are flying around. If we have not only, say, gas molecule A in there, but maybe we got B and C. I know my alphabet, so that's good. So it is flying around. Now, when we look at the total pressure, which is typically the atmospheric pressure, the barometer reading, it's a result of all three of those gases participating: gas A, the pressure of gas B, and the pressure of gas C. These are what are referred to as partial pressures, because each of them partially contribute to the total pressure of that gas mixture. Probably the most common way, or one of the most common ways that we can basically solve for the partial pressures of a gas is, frankly, just use the ideal gas law. And because in an ideal situation, we could assume that, it's almost like each gas is in there by themselves. All we have to do, frankly, is just solve the ideal gas law for each gas individually, and that will give us the partial pressures. Now, because they are in a mixture together, a couple of things is really nice for most of the values that we see here. The volume for each gas that's in that mixture will be the same because they're flying around in the same container. So usually this is the same for all the gases. Temperature is usually the same for all the gases because that container is sitting in the same room at the same temperature. R is obviously a constant. So typically when you have to do sort of a partial pressure problem, really the only thing in a lot of cases that you have to figure out is the moles of each of the gases that are present. So if you're given it in grams, you would use the molar mass to do so, which is, again, a very common way to do that. So you basically figure out the moles of each of the gases, plug it into the ideal gas law separately each time for each gas. And then at the end, all you have to do is add up each of the pressure values, and that will give you your total pressure that is in that mixture. So really, partial pressures is, in a lot of cases, just the ideal gas law solved separately for each gas that's present. As we see here, when our two gases combine, we get a mixture of gas. But again, these values will be the same for all gases that are in that mixture. So it works if you have, two gases, three gases. It really doesn't matter how many gases you have, but you basically just solve that ideal gas law each time separately for each gas. And that is sort of the beauty of the ideal situation, the ideal gases. Again, even though there's multiple different gases flying around the same container, under those ideal conditions, it's almost like they're not there. So that's why we could kind of separately do the calculation for each of these things. We don't have to take into account anything like the interaction between the different gas molecules in an ideal situation. So let's take a look at an example here. We have 5 grams of helium and 5 grams of neon in a 2.5 liter container at 27 degrees Celsius. what is the partial pressures of each gas and what is the total pressure. So we're looking for 3 answers. The partial pressure of helium from the periodic table, 4.003. The partial pressure of neon from the periodic table, 2018. And we're looking for the total pressure here. So take a few minutes there, see what you come up with. So once again, we have a mixture basically here of helium and neon flying around in the same container. Once again, because they're in the same container, the volume for both of the gases is going to be 2.5 liters. The temperature as well for both of those gases will be 27 degrees Celsius. And as we know, we should always convert that into Kelvin. So might as well just do that right here by taking 273. Going to give us 300 Kelvin in this case. At this point, we are looking really for the pressures of each gas. So we have P, V, and T. And if we think of like the ideal gas law here, P, V, and T, we do need N here as to what we're looking for to solve, so that we can get to obviously P that's over here. So to do that, we're going to convert our grams of each of these into moles. So we're going to take our 5 grams of helium. We're going to use the molar mass from the periodic table and divide by it. That's going to give us 1.25 moles of helium. We're going to take our 5 grams of neon. And we'll divide by our 2018 grams per mole of neon. And that's going to get us 0.248 moles of neon. Any questions on that so far? So now that we have the moles of each of these guys, which obviously in the ideal gas law is equal to N, we have pretty much everything we need to solve for the partial pressures. So we're just going to take, for example, for helium, the partial pressure, we're going to divide the volume to the other side. It's going to give us nRT divided by V. We're going to take the moles there of helium. We're going to take our gas constant, which again is a value we always have. We're going to take the temperature and we're going to divide it all by the volume here, which is 2.5 liters. Liters will cancel, Kelvin will cancel, moles will cancel. Going to leave us atmospheres, which is a pressure, and that's good because that's what we're looking for. And we will end up here with about 12.3 atmospheres. This would be what is referred to as the partial pressure of helium in this case. Any questions on that calculation? So we're just going to re-up it here and pretty much do the same calculation there for neon, except obviously we're going to use the moles for neon in this case. So if we did that for our neon, it's going to be nRT over V. And really the only thing changing here is using the moles of neon. Everything else here is going to be the same since they're in the same container. All divided by 2.5 liters. Once again, everything's going to cancel except for atmospheres. And in this case, it will give us 2.44 atmospheres. And that would be the partial pressure of neon. Any question on that calculation? Total pressure is found by taking those two numbers and just adding them together. Yeah, so we can get the total pressure here by just adding. So we got 12.3 plus a 2.44, going to give us a 14.7 atmospheres as our total pressure in this particular case. Any question on any of that calculation? Pretty much just the ideal gas law for each gas separately. Volumes and temperatures will be the same. The one that's actually contributing the most pressure here is which gas? It is helium. Any ideas why that would be? It is because helium is lighter. Yeah. So it is lighter, which means it will be able to fly around a lot faster, actually have a much higher velocity than this heavier, slower moving neon. So that's why it contributes to more pressure that we see in this case. Any questions on that? When you take 1A, you'll calculate the velocity of something like that in these conditions. All right, so this is one type of partial pressure problem, which pretty much just feeds into the ideal gas law. Now, in some cases, you may be given not really enough information, for example, to go into the ideal gas law. So maybe the only thing that you're given are moles, are a way to get to the moles of each gas that are in a mixture. And if you are given something just basic, no temperatures, nothing else sort of given to you, but you have just the moles, are able to get to the moles of each gas. And the other piece of information that you would need is something about a pressure. So maybe you have one of the partial pressures of the gas given to you. Maybe you have the total pressure given to you. So if you're able to get to the moles and you have one piece of pressure information given to you in a mixture, you could actually still solve for partial pressures by using what is sometimes referred to as the mole fraction. And the mole fraction is kind of like a percentage without multiplying by 100. So it's basically the moles that you're interested in divided by the total moles, and just don't times it by 100, basically. That's what the mole fraction represents here, X. So if we have this mixture of two gases, A and B, and we're interested in the mole fraction of A, we would take the moles of A, we would divide it by the total moles, and that will give us our mole fraction. And that works well with this formula here, which is, again, one that you could use if you're in that situation where you could get to moles and you got one piece of pressure information given to you. That is the partial pressure of a gas. So that's the partial pressure is equal to the mole fraction of that gas times the total pressure. And that's the total pressure there. So this is a nice sort of workaround sometimes. If you're sort of limited on information, but obviously in order to use this formula, you would need at least one pressure sort of information given to you. Any questions on that there? So let's take a look at one as to how this sort of works. So in this case, we got the moles of CH4 given to us, a little ethane and a little propane. So we got three different gases basically floating around in there, and they gave us the total pressure. And we're looking for the partial pressure here of propane. So in this case, we could take the partial pressure of propane from our formula would equal the mole fraction of propane times the total pressure, basically. So we could calculate the mole fraction of our propane by taking the moles of propane, which in this case was 0.116. And we're going to really just divide it by the total moles, which would be 8.24 moles for methane, 0.421 moles for our ethane, and 0.116 moles for our propane. So that's basically our total moles there. And if we do that, we would take 0.116 divided by what we get there on the bottom when we add it all together. Looks like we get a mole fraction of something like 0.0132. Now that we have the mole fraction and they gave us the total pressure, we could find the partial pressure in this case by simply taking that, which truly is a percentage just left in decimal form, so you don't have to convert it back to a decimal really at this point. It's basically 1% this times our total pressure of 1.37. And that would get us a partial pressure of 0.0181 atmospheres for our propane. We could do the same thing for the other gases in this mixture. We would just obviously take, for example, if we wanted the mole fraction of methane, we would take our 8.24 moles and divide it by the total moles, which is 8.777. So if we did that, 8.24 divided by 8.77 means that basically it's 93% there pretty much of methane floating around, which means the partial pressure of methane in this case would be 0.939 times our total pressure, 1.37. Gets us a pressure of 1.29 atmospheres. So we can see here just from doing methane, it is really the major contributor to the pressure in this situation because there's a lot more moles of it flying around, right, compared to everybody else. So in this case, there's a lot more moles of it flying around. In addition, it's also the lightest of the three. So it's going to be flying around a lot faster and there's more of it. And that's why we see it pretty much the major contributor. So this is a nice little formula. Again, just keep it on the side if you like, in a situation where you can get the moles and you have some type of pressure information given to you. Other than that, probably the ideal gas law is most of the time what you would probably use, but this is a nice workaround if you're sort of limited on the information given to you. Obviously, we don't know anything about the temperature, right, or the volume in this situation, so there's no way to kind of use the ideal gas law. So that's why we would have to use something like this sort of formula here. Any questions on that there? Okay. Now let's talk about a third type of partial pressure situation, which is essentially the experiment we're going to do in about 20 minutes here, which is this one. So if we take something like potassium chlorate there and we heat it up, it is going to go through a decomposition reaction, which means it's going to make a little potassium chloride and it's going to make some oxygen gas, right? And we probably should do a little balancing, I suppose, there. Like a 2 there, maybe like a 2 there, and 6, maybe like a 3 there. I think maybe I got it balanced. That's good. So in this particular case, as we heat it up, the oxygen gas is going to travel and it's got nowhere to go, but obviously down through the tube. And we have this big jar full of water like you will have before. The hydrogen gas will start to, the oxygen gas in this case will start to bubble up. The water will come out and we'll get like that empty spot like we had in our big tube the other day or last week. And it will have our oxygen gas. Once again, though, as we can see, we're kind of collected in a water environment. So the result of just the reaction sort of occurring is it's going to heat up some of the water. So in addition to that oxygen, we are going to collect some water. And that is what is referred to as water vapor. And if we're doing this experiment, we're really only interested, again, in the oxygen gas in this case. So we're really only interested in that guy. So this makes a partial pressure situation that occurs where the pressure of the gas you're interested in, as we talked about last time, is, say that again, the total pressure is equal to the pressure of the gas you're interested in plus the vapor pressure of water. So that's the vapor pressure of water. And much like what you did obviously in the lab and you'll do again, you get that value from a table, which is again based on temperature. And in a lot of cases, because we're interested in just the oxygen in this particular case, we do have to do sort of a corrected calculation for the pressure so that the pressure we're using only deals with the oxygen's contribution rather than the water vapor's contribution to it. So in a lot of cases, there's our table that you could look up and you can also find in your book. We could take the total pressure equals the pressure of our gas plus our vapor pressure of water, which comes from a table, and we could rearrange it. And that means that basically we're just going to take the total pressure minus the vapor pressure of water. This, much like it was listed in your lab, is sometimes referred to as like the pressure of the dry gas because you're kind of subtracting off water's contribution to it. So you can think of this as sort of like a correction calculation that you oftentimes have to do whenever you're sort of collecting your gas with water involved. And the key words in a book type problem that you know that is sort of this situation is it will say something like the gas was collected over water. The gas was saturated with water vapor. So something mentioned like that. And the problem means you probably got to go find a table and look up the vapor pressure of water and then obviously do your subtraction. Any questions on that there? So let's take a look at one here. If we collected oxygen gas that is saturated with water vapor at 30 degrees, the total pressure is 753. The vapor pressure of water at 30 degrees from that table is 31.824 torr. What is the partial pressure of oxygen in atmospheres? So the key that I know that this was, again, sort of our partial pressure situation where we're collecting it with water is that sentence right there. It is saturated with water vapor. So that tells me I have the total pressure going to be equal to the pressure of oxygen gas in this example, plus the vapor pressure of water. Once again, if it was not given to you based on temperature, you would have to look up that value. And that means in this case, our total pressure is 753 torr equals the partial pressure of oxygen plus 31.824 torr. We're going to subtract that to the other side. Gonna get rid of that. And that will give us a partial pressure of just the oxygen's contribution here of 753 minus 31.824. That's going to give us something like 721 torr. And we do want it in atmospheres, which means 760 torr is an atmosphere, right? And if we do that divided by 760, going to get us 0.949, looks like. So that value, along with this value here, is the pressure basically of the dry oxygen gas in the situation, taking out water's contribution. So that's a very common correction that you have to do, especially in experiments where you collect that gas with water. Any questions on that there? Okay. Question on partial pressures. We saw three different sort of partial pressure situations. Okay. All right, we will lay it up there at this point. We're pretty much done. We've got a couple of slides, so we'll finish them next time, I think.